Creating an operating system, Part 2. In the last episode, I started work on InfernoOS, and I got some basic graphics working for it. The next thing I was going to work on was really fonts, right? And in order to do fonts, there's a good change that I want to do, because I think we have matured enough to be able to make that change. That change here is the jump to 32-bit mode. But first of all, what is 16-bit and 32-bit? Bits are essentially just ones or zeros, and these can be combined together to represent basic numbers and information. So obviously 8 bits, 16 bits, 32 bits, and 64 bits are all just defining the number of bits that they encompass. And information on computers can be imagined as traveling on a highway. The size of the highway can change how many bits are allowed to travel to it at a time. These all refer to the number of bits allowed at a time and the number of memory it's allowed to have. Right now we're using 16-bit, which gives us 64 kilobytes of RAM and processes data in 16-bit chunks. But if we switch to 32-bit, we get 4 gigabytes of RAM, which is way more. And then we also get to process data in 32-bit chunks. So we want to switch there for more memory and then do fonts. But first of all, how do we even switch to 32-bit mode? And we do that via a GDT, a global descriptor table. GDTs are responsible for defining memory segments and adding privileges to make sure that no user controls the OS. It can also change how some instructions are ran. So let's make our own GDT. GDTs have segments. Each segment is defined like this, where the base is where physical RAM in the segment starts, and the limit is how large the segment is. There are 3 segments: the null segment, which is always set to 0, the code segment, and the data and stack segment. Then we need a GDT descriptor. And to change a register in order to actually switch. Okay, so now that we know what a GDT is, we can actually start working on our own. And we can just make a simple GDT that has them here. We can start planning our GDT. So the first thing we need is 3 segments. We can start with some sort of a GDT start, and then we can continue and add more fields. But first of all, I'd like to tell you that this is not really that easy to do, to be honest. It took me a lot of time to find the information. So if you like the type of work I'm putting into this channel, please like and subscribe. Anyways, so we have a GDT start. Then we could have a null segment, I think. And null segment's just all 0, so we can have I'm pretty sure it's just a D, I believe. Anyways, I'll just keep it like this, I guess. And then we can start with the code segment. Now, we're gonna jump to 32-bit mode again, and we gotta look at this little graph here, so we can decide what our limit in base is gonna be. If you look at this diagram over here. So we can say our limit will be 0xff. Our base will just be 0, and then our limit will be whatever the maximum value is for a 20-bit integer. So just a bunch of FFFs, probably something like that. So if we just start doing this, we need 0 to 16 bits of limit to start off, and that is 2 bytes. So can go ahead and do something like that. Then we need the 0 to 24 bits of base. So in order to do that, we could split that into two things. First of all, that's 0 to 16, and then the 17 to 24. So just do another. Actually, here I think I messed up. I think we want to have something like this. And then over here we just have a 0. Then we have another db 0. Then we gotta put in an access byte. So we can look at the flags here, and we can decide. So first of all, is it gonna be present in memory? Yes. And we're in the kernel, so 0, 0. This is a standard memory segment, so I think it's a 1. Yeah. And then code can be executed. And since it can be executed, the next bit will be a flow of privileges can run this code. So we don't want that. We can turn that off. And then RW, we want to read and execute to this. And then starts at so we just this is always going to be that. So you can put this all together: 1 0 0 1 1 1 0 1 0. That's just our first thing. And then once we're done with the access byte, we have more to work on to. That is flags. So firstly, we want way more than just this amount of memory. So we want to multiply this limit by 4 kilobytes. So it would be whatever this number is, times 4 kilobytes. So we have a bit more, way more memory. We could turn that to, we could turn that on. We want 32-bit mode, but not 64-bit mode. And ignore bit 3 free space. We can just set that to this. So we got 1 1 0 0. And then after that, we have like 4 bits of the limit combined with 8 bits of the base. So this is just like less than. So I think I actually made a mistake here because this is less than a byte, right? So we need to add something else to this. So that's the 4 bits of the limit. And I'm pretty sure the way that this whole system works, it's well, if you have a 255 is the last byte of this combination, we can assure that. Maybe 256, I actually forgot. And we're in a base 2 system. The binary is a base 2, I believe. So it would just be a bunch of 1s. However many, I don't know how many that is. So the last 2 bits must be 1 1 1 1, just 4 1s. And then we can just add that combination at the end. There you go. And then we just have 8 bits of base. So 1 byte of the base, which is just 0. So that is a code segment. Now we need to plan what our data segment will look like. So now if you look at this again, we can decide why not just have the same base and limit for the data segment to make it a bit simpler. And that also means that a lot of this stuff will be pretty similar. So also gonna have to define these dw0 db0, but now this comes a bit different. So we gotta look back at the access byte. It's always gonna be 1, still 0 0. I think that would be a 0. And if code can be executed, I don't think we should do that on. So 1 if addresses go down, and 0 if they go up. So I feel like on the stack they usually go down, so I might be inspired by a bit of that type of format. And then a read and write, a write only, we definitely want it to be that. So it's read and write, and obviously starts at 0, so like always. So then we got 1 0 0 0 0 1 1 0, and we can turn that. And we still have the flags and then the bits. So we know from this one that the last 4 will always be this. So we can have something and then 1 1 1 1. But for what that is, granularity, 32-bit mode, 64 4-bit mode, and ignore space 3 bits. So we got our next one, which is 1100 1111. So I think that might be it because we have those segments, but we still have to build the descriptor. So and I have no idea how many bits are in. It feels like probably the 3216. We might have to go back to this, but for now we could just assume it's a DW, and we can put that. Maybe we could have a GDTN marker here. I don't even think we need to put these markers here. Like we should probably signal though. So null segment. Well, I don't think we need to for now. We might need it later. And then data segment. So all we need to do is GDT end minus GDT start. And I'm pretty sure there's a -1. I don't know. There's some way you're supposed to format that actually. I don't know how that works. And the address of GDT. So when it starts, that's just GDT start. It's pretty simple. And we have to set CR0 to 1 to turn on protected mode. But let's just, like, how is this GDT working out so far? So I'm probably going to research some more and check if this is how it's supposed to ideally be and compare it to other OSs. But I really hope that this one is what works. And, see if there's any errors with this, like 1111 or something like that. I don't really want to put these on video because, like, I plan for this to be like a short series. I don't want to have too much like researching in the background. But I think that's what we have for GDT. But yeah, there's only one way to find out. And I'm gonna probably include this. Like sometime soon. I don't even know I have an Amstrad. I mean, we're not using that. But we also need to work on one more thing, and that's like hopefully making this whole window a bit larger. So I think I found some things that might be an error in my code. So I found out that the GDT descriptor is supposed to be I think 32 bytes. What we have right now is 16. So I think that means we need to change these to define double words, which I just realized I didn't like mention what they are. Each of these are 16 bits. I believe they are. Anyways, I'm pretty sure also here there was one setting. If it was a standard memory segment or a special one. So I set this over here, and I set this over here to 0 in the data segment because I thought that it wasn't special. That it was special, but like what it means by standard versus special, pretty sure it's just a standard code and data. I really thought it was a split between code and data, and I thought the data meant special, because like it's, I don't know, if something about it feels special, it's just like memory that's being stored. But that's my bad. So it's actually 100101110. But with all that said, I completely forgot I was supposed to initialize the GDT. But there's one instruction that I know. So we got to LGDT descriptor. And we have to jump to me. And maybe in the kernel. Should have something like this over there. And so after that, CR0 needs to be set to 1. So I believe that's it. We spent a null segment, code segment and a data segment, and we have a descriptor with double words, and we have a main that CLIs LGDTs. So I think what we have is good. I believe move CR0 equals to 1 is move CR0 and 1 is done after LGDT. I hope that's a valid assumption. Again, I don't want to show like the research that I'm doing behind the scenes to get all of this done. But I just want to let you know that there's a lot of work going on. So I know I've said this before, but please like and subscribe, because I want to know if what I'm doing right now is right or if I should change it. Anyways, thank you. So I found out some more things. And I think I know something else that happened a bit wrong, and that's like the byte after like the executable one. I forgot where that is. So, yeah. So here, I said why don't we let's let them go down, and I like switched a little up, and it realized that in most OSs they're supposed to go up. And I don't want my OS to be like the sole thumb out of every other OS. So, I mean, I guess we could change that. And then we gotta find the one over here. So, and I think that's it. So, and then we can continue on getting everything to work. So I think this one is also considered supposed to be a DW. So I think that means that I put the data a bit wrong. So it's supposed to be I think 32 total. Wait, I don't know. I don't really want to check. So, anyways, we do this thing over here. And I don't know why I was supposed to do this, but I just found it. That like in operating systems, you do something like this, or I don't know. You're supposed to switch the last bit. I don't know how you're supposed to do it. I'm pretty sure you're supposed to switch the last bit. I don't know how to do that. And then we got to jump to a specific region. That region is, I think, the code segment minus the data segment minus the code segment. So the size of the code segment. Wait, no, I'm pretty sure it's the code segment minus the start. But the fun thing is that that's hard coded, right? Since each segment is, if you measure it, 8 bytes. I believe it's 8 bytes. Yeah, it's 8 bytes. So we know that the code segment minus the start will always be 8. So we might as well just put like 0x8. Okay, and then we have some sort of a new, we have to do a long jump here. The reason a long jump is done is because there's a specific register in assembly. I'm pretty sure it's called like the CS register, and it's basically unchangeable. It's a very important register, so in assembly you can't really change it. But there's only one way you can change it, and that's through this type of instruction, which we have this. We have a jump, but it has something before it with the colon, and that changes that specific register, and that's why we use it. So we can change our bits to 32 after this. We can make some sort of a start. I think usually the convention is start is where it truly starts, and main is where your code begins. So you can jump to that and change that register and go to main. And then all we have to do in main is we just move a bunch of registers. So AX needs to be 0x10. So I don't know why it's that. Might be the data segment, actually. I don't get why there's like, we're in hexadecimal, so which is a different type of numbering system. So it would be 90F, something similar to that. And there's 16 total. So yeah, I don't think this is it. I'm pretty sure it's just a data segment though, but it's some hardcoded value. Then we just gotta set, just literally gotta copy this code like multiple times. So ES, FS, GS, int SS. Now that we're here, we can try to see if this will run. So maybe we can get some sort of a, we can switch it to GDT. How about we switch it to GDT? Then we can run here. So we have multiple errors. 47. We could set that to a temp register. So EAX. I don't know how we or EAX, and then just move that back over here and do that. So 55. It won't let me set those registers. But why is there no problem when you do that? So it just wants me to like set all of these to one register. Okay. Well, it's constantly booting and starting up again. I don't know what that's supposed to mean. We can, how about we have an infinite loop here? So we jump to our current address, then we jump to our current address again. Okay, so I think I figured out what the problem was. We needed the last byte, 8 bits of the base, and I forgot to include that in the data segment actually. So I'm pretty sure if you run this now, yes, it just works. I wonder if we could like zoom to fit. So maybe we have to remove a 0. No. So maybe there's an extra 0. Wait, that's a green pixel. So, we've done it. And actually, I want to switch to 64-bit mode sometime soon, but like it's harder to do. There's a lot more stuff behind it than just creating a GDT. So, if you want me to, please subscribe so I know what I should do. Maybe we could also, instead of VGA, we use a linear frame buffer. And the way that would work, I'm probably gonna remove this loop. And then over here, we do something like this. We have a CX, which is like a linear frame buffer thing. And then in DI, we have some address. So, like frame buffer info. And then that is some sort of a DD. Then over here we use that. This the address of the 2 frame buffer will be this plus 40. So then we gotta do something like for FO2, which is what we did over there. Move BX UX 4118, and maybe move CX this. And then int 0x10. Now let's see. So it does not seem to be working. I don't think we need this. And the data in this frame buffer info is supposed to be 256 bytes. So if we have a DQ, that's 8 bytes. So just have to replicate this 256 divided by 8 number of times. So you have to copy and paste 32 of these. and we have a blank screen. Now maybe we could go ahead and go into framebuffer info plus 40. Oh, that's the, so then we can have a framebuffer, which is just a single, I think it's a DW, because I mean we can just allocate extra space. I don't really then no, so we go there, here plus 40, and then move framebuffer, and you just move that to EAX, and then we can move, I don't know, 256. Okay, so byte exceeds bounds. More like this. So we can move the frame buffer here. Then we can have some sort of a loop. And then we can compare EBX to 1000. Then here, increment EBX, increment, yeah. Then after this, and if they're equal, if they're not equal, keep going in the loop. Shrinks down. Whenever you grow it, it shrinks down. So that's not really what I want, though. So I think we have to get the data in framebuffer. And wait, that's something. So we have small lining here. RGB, we can add an extra one. And we can switch the limit to way higher. So we can fill the screen with different colors. So green and blue. Red and blue. So instead of a VGA, we're stuck with like just a couple of colors. We now have a full 255, 255, 255, which is pretty cool. So I think there could be a way to work on fonts like in an easier manner, because right now I'm just like using assembly for everything, and I really hope that we can get C running on here. I mean, I think we might as well start. But in order to do that, we should probably have like a separate C folder, and then we have some sort of main.c. So for some reason it's not putting it with the syntax highlighting. I don't think we can have it. You can't have any libraries. So I guess we can have something like this. We need to get this code compiled. Maybe this main.c unsupported architecture. So maybe we don't want like it to be with anything else. There you go. That is a command that creates a main.o. But we want a main.bin. Let's look over here. So NASM just automatically compiles to a bin. Is there something like GCC main.o into main.bin? We want it, so this is the ELF file. Intel 386 main.o into a main.bin. O format binary. Okay, well we have one command working, so let's just like get that. And then once we do this over here, we can then move main.bin, kernel.bin, and main.o. So cannot open main.bin or such file or direct. Oh. So what we can remove is bootloader.bin. So that's our empty program that we have earlier. We want to add this. Now I'm pretty sure NASM has a back end to output into these .o files. But I don't think our code is meant to work for that. All of these are .o's and they're switched to a .bin at the end. Or we could, I think that's elf32 .o. And we could put this into a main.o like we usually do with freestanding, and then we can merge together these two. And then we can finally get this into kernel.bin, and then put in binary. Instruction found, an unknown instruction accepted. So it doesn't like that. So it won't let our address be over there. Maybe you could just put this into a bin, then just convert this into a main.bin, and we have one more thing. Pretty sure we just merge these all together like this. Oh, so C kernel. Then C kernel.bin. Unknown option O format. So do we have like an i386 GCC? You know, x86 64. x64. So okay, maybe we weren't that close. Cannot find entry symbol underscore start. Okay. Start. Maybe it needs to be an underscore start. There we go. And we're just bringing this to an end. Maybe we do. Okay. It really depends on how arguments are being parsed in this version. Because we do want to give some arguments over here. So we can just start with a kernel underscore C. And then we can move EDI, which is I'm pretty sure the argument, to our framebuffer. Pretty much the only argument we need to give. And then we can give ourselves a void times framebuffer. Just say framebuffer 0 is equal to dereferring. Okay, so maybe we can have some sort of in char times. No. Oh, maybe we need to call it. I don't see a pixel over there. Maybe we can have some sort of a loop here. We keep getting. So no, I don't know if we're really calling that data. So we need something that defines where our underscore start is, because we want to make sure that our underscore start is right next to the code in the .o, so a comfortable place. And maybe that's like an extern. Maybe that's some sort of an extern underscore start, and then we call it binary output format does not support. Okay, so we don't support that. So we want to make sure that it's a very simple request, but we want to make sure that the underscore start is right at the start of this C underscore kernel main. Is C underscore kernel that bin. Maybe you could have like a link with a linker. But I don't know anything about linker.ld, and that's in its file format. So why don't we just start doing that real quick? So, and all I know is entry start. And just goes, okay, so this, and it doesn't, yeah, so we're right where we want to be. So we have a sections, okay, and that's so there's syntax highlighting here, so I know what I'm doing this, right? So we can load at this point. And then keep, oh, so we force something in the text. We can show the order. So actually right after this, so everything in the text, everything in the text will be right over here. And we can keep a label to be before it. Oh, and that's where underscore start comes in. That's where we want that. No. So I think these are the sections in the output, and these are the sections inside of the C code. So we can do like the same with these things, except all we have here is just gonna be that data, and then we could do the same with BSS and raw data. I don't know what that is. Read-only data. Putting the data at a specific address. That's where we are. Why do we put something like this, and then we said call this specific place? No. Maybe a jump. Still. No, maybe we can move this stuff into a separate file. Because I think we're out of the GDT stage. But we're still doing something like this where we jump to main. Hi. So I'm definitely not gonna show the footage of how long it took for me to finally make this work. But it does. It actually does. And we actually have something that works. So we can actually fill up lines and actually fill up text. That took like a lot of changes, and again, I want this to be more focused on like the triumphs of this operating system journey than like 30 hours of just researching stuff. But anyways, this is the point where we can finally work on fonts, but this time we can actually do it better, because now we have C, and we can now do everything we wanted to do in assembly directly in C, which I think will make it a bit easier to create a font, in my opinion. So we need simple font formats. Okay, so looking at the hextemp, I think I know some things about this file format. So obviously as seen before, we have this magic, and I'm pretty sure these are in the weird order, so it's actually 3604 and then 0010. So I think we're gonna get started. So we just need to read the data at this position, which will be, if this is 900, this would be Not 13. It's actually not 13. We could actually do some hexadecimal math over here. Yeah, it's DOO. So, because of the way hexadecimal works. So we have a bunch of errors. So excess elements and scalar. Oh, okay. So it's supposed to be a so we want to put all of this here. Bucket identifier. Okay, so we have it all working. And the next thing we need to do is actually read out of this. So I believe these are in reversed order. Yeah, that is kind of weird. Definitely, because these are reversed. Because they're actually it's actually 0x30, I believe. What would happen if we just did all of this with C and we went to the start? 3604, 0436. So that's kind of annoying, but we can create a new macro. And what we do, so VW, then write run delete W A space. And would that work if we repeated it? So reverse it. So and we're gonna repeat this 1,000 times. And you can see it like moves audibly. And it's a really cool animation actually. Once we did that, we can do a very simple trick. We can just we can actually run this actually. So it has that. We can do this only if PSF underscore font 0 is 0x36, which should happen, yes. And it's not 0, yeah, so we have something actually working. And then we can try to split this into a function, maybe. That load a font, maybe? Let's just have some sort of a PSF load over here, and it returns an int. So it just loads the given address in memory. It just loads the hard-coded. So if it's if it does not start with that, we return 0. Or the first one is not 0x04. So int PSF is equal to PSF underscore load. And if PSF is equal to 0, we do that. It does not work because we have a valid file. And O is not equal to, so because I think we're calling PSF load. So I'm pretty sure kernel.c has to be at the start. So this can be after and it can be initialized here. And we can do it like this. Yes, and it still looks showing that our font is actually valid. And the next thing is pretty sure if it's 256, if it's 256 bytes. So we don't support 256 character mode. And then character height is PSF font 3. And that's actually plus. And then we can take all of this and treat it as though it's a byte actually, so it is actually normal. We don't have to do anything special about that. And we have glyph count 128, so actually I believe it is. So 256, we don't support 512 character mode. And then after that, what do we want to return? That's actually a good question. So maybe we could just have a simple thing where we send the rendered stuff in a glyph in a certain number. So say we send 0, and this is not PSF equals 1 anymore. And all we do here essentially is if a glyph n is greater than a glyph count, then what we want to do is we just want to switch glyph n to 0. Okay, switch it to the glyph count. And then all we do is we don't return 0 here, we return null. If PSF is equal to null, then we just return -1. And then glyph n is equal to glyph count, and we return PSF font plus, because we want to keep a pointer. I believe 4, yes, plus 4, and then plus character height times 8, which is that, and then times glyph n. There you go. So we should hopefully we can actually create a very simple, have a int fill, and also we don't want to truncate this anymore. We're not doing that. We want to remove that. And then in this fill function, that takes in that, we can essentially just do this. And that means that we can actually have a first error screen. It's just gonna be 255.0.0, and if all does go well, we can print green. And then okay, so okay. So we just have this, and then that over here. std def So we don't have anything. We just gotta do char times 0. Then, okay, any instances of null. So char times 0. Void value not ignored as it ought to be. Char times frame buffer. Oh, okay, so we do need to have some sort of a frame buffer that's being given. We have a green screen, which means that it all worked, which is actually really cool. And once we have that green screen, so if we have this, we want to also return -1. So it's the, yeah, okay. And if we have passed it all, we do still want to have some information about the character height. So maybe we can have some sort of a character height over here. And if we have this, we can also actually do char times 0 because we're getting an invalid character. What we can do here is we can actually do add character height. So and then if height is not equal to int times 0, then times height is equal to character height. Pretty sure it's the only variable we'll need. Okay, so okay. There you go. And now that we have a character height, we can start printing stuff. 8 is hard-coded. 8 will always be the width. So then we can have some sort of a font I is equal to 0 in character height. And then this to 8. Now I just gotta have to find out how this system works. So you could think of it as in groups of 4. Wait. Oh, never mind. So each byte is always a certain character. And then we can actually put that. So PSF it with Y will be the current character. And then what we need to do is bit shift it. I believe in this direction. Hopefully I'm not wrong because. And if that is right, we want to write at that address. So void fill pixel with a and if x is greater than 1024 or y is greater than 620, then we just return. And then we want to do just this code. And then if it is true, we can fill the frame buffer with white at that certain character. Return in the function returning void. Load, when we're loading the PSF, we might want to load it with the character H. So I think I found some problems. So this is not supposed to be that, and then we can temporarily move the fill. And it's still not working. So it says, okay, so might be 7 minus. It's probably a bit to the right, isn't it? And that's an actual character. We can print actual characters. That's actually really cool. But that's essentially what we have. And that's pretty good for how much have we spent? That's 100 lines of C code that we just started on. So, I mean, that effectively means that we've switched to 32-bit mode and we've added fonts. And so then we decide if we want anything else in this episode. I think I might end it here, maybe.